Well, this is John Black, Super Chemist. As promised, I'm going to tell you how to make blue light between 450 and 480 nanometer. As we discussed in the last series of videos called benzyl chloride via free radical halogenation, we need between 421 and 494 nanometers. So this would be perfect if we could just make this wavelength light, or these range of wavelengths, and only that range. And we said that UV was actually too strong, not for any other type of chlorination, but for a benzyl chlorination. UV is actually, even violet light, is too strong for the reaction. But I want you to look at this. Here's what we need, right? 421 to 494. This is green light. This is blue light, I think. It might actually be violet, I don't know. But up here would be your UV, and this would be green and all your longer wavelengths, like, orange, yellow, and red and all that. But why did we want 421? Why didn't we want any UV rays? Was because at 421 nanometers, or anything lower than, that, you're going to get any shorter wavelengths, you're going to have enough energy to break these benzyl carbon chlorine bonds that you're making, right? And we figured it out for 400 nanometers. It was this many joules per bond that a photon will give you, and it was this many joules per bond to break this bond, which you can see that 400 nanometers is a bigger number, so it's more energy than is even needed to break this bond. But look how close it is. 4.7 and 4.9. That looks like it's very close, but it's actually even closer than it appears, because, and that's why I wanted to bring this up. This is times 10 to the negative 19th. So let's not use scientific notation. Let's write out the numbers. This number is right here, and this number is right here. That's 18 zeros, right? Because I had a decimal point was here. I had to move it over 1, and then add 18 zeros because I had to move the decimal point 19 times because it's to the negative 19. Now look at how close the numbers are. Like 4.7 and 4.9 seem close. But these are like the same number. You know what I mean? Because think about it. These are fractions of a 1, right? This isn't even a 1. But if you had a 1 here, that would only be 1,000ths. Over here would be 1 millionths, 1 billionths, 1 trillionths. So if there was a difference over here of 2, it would be 2 trillionths, not 2 trillion, a fraction, 2 trillionths of a difference. That is like nothing, okay? And now you're way over here. I don't even know what these numbers come. I don't even know how to name these numbers up here. But that's the fraction. It's only 2 whatever, not 2 trillionths, but because 2 trillionths would be way down here. Whatever the number is called for up here, it's that fraction of a difference. They're practically the same number. You know what I'm saying? I just wanted to bring that up, how really close they are. This makes it appear like they're close, but if you really think about what these numbers are, I mean, they're almost the same number, okay? But also keep in mind that 336 nanometers to 400 nanometers of UV light does get through the ozone and through the glass from your apparatus. And these 336, up to 399, they're higher energy. So there's even going to be more energy. And you only need exactly what this is. If you have exactly what it is, it's going to break the bond. But it has to find that bond. It has to hit it in the right angle at the right. Everything has to be perfectly lined up and blah, blah, blah. So keep that in mind too. The sun will work. It's no problem. And also keep in mind also 400 to 421 nanometer, which is mostly violet light, if not all violet light, will also break these bonds, right? So I just wanted to bring that up. That really has nothing to do with this video. but I wanted to see how close, you know, using the sun, it's not like you have a billion times more energy than you need for the bond to break, but you have a slightly more, you know what I mean? And these will even be more energy, so the shorter the wavelength. Alright, so I promised you this blue light, and I'm going to tell you how to get it, right? Here's your nanometers, here's your, you know, the shortest wavelength that can get into your reaction, here's UV, all this is UV. Here's what we want though. See how I got the lines, the orange lines going down? 421 to 494 nanometers. That's what we want. And guess what blue LEDs produce? They produce between 450 and some people say 475, some people say 480. So I put 480 just in case. But you can see that it's in between, right? In between this and this is the LED. And I mean, in actuality, it would probably be more perfect if it was 430 to 480. That would actually be the most perfect that you could be. You can be more perfect than that. But 450 to 480 is, or 475, either way, is good. It's blue light. Why it's great? It's because you know it's only blue light, and that's it. Okay. You know, when you do a free radical chlorination like this, you know, a benzyl one, you need to turn off all the other lights and block out the sun. If you have any windows, you know, curtain them up. If you have an overhead light or any other fluorescent lights or incandescent lights or any kind of lights, turn them all off because they are producing small amounts of UV and violet light. So it's that simple. You just buy a bulb that you can screw into a regular lamp or whatever, regular light socket. That is an LED light that's blue. It has to be blue though. Okay. Now, remember if you watch my, you know, the benzyl chloride via free radical halogenation, you'll know that I talked about intensity, and I said if if you only have 1 photon per hour coming out of your bulb or your light source, you know, that's going to take you forever. You know, you'll be breaking one bond a second. It'll take, you know, forever and ever. So intensity plays a part. You need it to be strong enough. It's going to do, being blue light, you know, that makes it strong enough to break the bonds, okay? But how many bonds you're going to break every second or every hour or every minute depends on how many photons you're actually throwing out there. You know what I mean? If you only have one wave with 1 photon, or you know, then that's, you know, you need a bunch of them. You need a strong power, you know, to produce a lot of wavelengths, not just one of blue. So how do we know what size to get? Well, let's look at this. All right, the sun. Okay, and it depends on the time of day. All this information here, I'm just guessing and winging it and estimating, because I don't need to be perfect, and I'll tell you why at the end. You'll understand why. It doesn't have to be an exact science on, you know, sizing this bulb, on how much power or wattage you need, how much intensity on the light. You know, it depends on the time of the day and who you ask. You know, some times of the day it's brighter than other times of the day. But on average, let's just say, and I made it 100,000 because it's easy math, okay? 100,000 lumens per square meter, okay? And lumens is just light, basically. It's certain candelas, that's it. Or candela per area, basically, I think. Don't quote me on that. But anyways, I divided it by 100 decameters per square meter because I want to know how many lumens the sun hits on the earth in 1 decameter, okay? And the reason why is because that's about 4 inches by 4 inches, okay? And, or 1/10 of a meter by 1/10 of a meter. And that's about the size of, you know, a 500 milliliter flask. And if you use a 1,000 milliliter flask, you only fill it halfway up, right? Which is 500 milliliters. So that's, you know, that's why I wanted that particular area. and it comes out to 1,000 lumens per decameter, square decameter, right? So this should work on anything, you know, like I said, I would not even do an experiment that big, so, you know, this is definitely going to be good for me. Keep in mind, this sun intensity that they say 100,000 lumens per square meter, some people say 108,000, some people say 96,000, whatever. It only takes into account visible light. It doesn't take into account UV. It doesn't take into account, you know, infrared or any of these other non, you know, invisible, all these invisible light ranges. Only takes into account visible light, right? So more than 1,000 lumens, say, of energy or light is getting into our reaction that they're not counting. They're not counting the UV, right? But they are counting orange light, you know, red light, yellow light, some of the green light that doesn't, you know, these lights, these wavelengths, they're not strong enough to break our chlorine-chlorine bonds. They're no good to us. So them including them into the lumens is useless to us, right? Now, I'm not saying they cancel out, and I didn't do any math or anything about it because I don't care, and you'll understand at the end why. I don't have to be exact. But let's just say, even though I don't know, but I'm sure it's close enough, that the UV light that it doesn't take into account with cancels out those longer wavelengths like red and yellow and some greens don't help us. You know what I mean? They're counting those in here. We don't need those, but we do need the UVs, right? But they didn't. So let's just say they cancel each other out, and we need 1,000 lumens. I'm guessing. Okay, this is my way of thinking. Is why I'm sizing my bulb the way I am. So there's 1,000 lumens, right? It says per square decameter. And I'm going to put the bulb right up to the reaction, you know what I mean? Like I said, I'm never going to have a reaction that big using a 1,000 milliliter flask. So this is definitely good enough. Now I want you to look at this chart. And all these charts online, they're all kind of screwed up. They're all close, you know what I mean? But they're not perfect. But like I said, we don't have to be exact or whatever. Now what this chart is telling you is this is the watts, you know, like when you get a regular light bulb, right? You know, you get a 100-watt light bulb for your room. Some people get 75. That tells you how much light. You know how much, you know that system. Well, this right here is lumens, right? A 40-watt will give you 450 lumens, a 6,800 lumens, a 100-watt will give you 1,600 lumens, and so forth here. Now, we just said about 1,000 lumens is what we want, right? So that would put us at 75 or higher. So I would want 100-watt light bulb, or LED equivalent to a 100-watt light bulb. And here's the equivalence thing right here on there. 40-watt regular light and a 4-watt LED light both produce the same lumens. They both produce the same amount of light, right? Same with a 7 and a 60. They produce the same amount, 800. Well, we wanted 100, right? Because we want more than the 1,000 lumens the sun puts out. We want at least 1,600. That's a 15-watt LED, so that's what I want. But, okay, and this is why it doesn't matter to me that to be exact or whatever, because look at this. Walmart has a floodlight, right? That's another thing I wanted to bring up first of all. You don't want to get a LED that looks like one of those incandescent lights bulbs, you know what I mean? Because that's going to produce light going all over the place, you know, three-dimensionally out as a sphere, you know what I mean? You want a floodlight type bulb that looks like this, you know, a floodlight. You still want the kind that screws into a regular, you know, light. But you want it to be LED like this. That way you can shine. You can have your reaction right here and shine this right, you know, directly into the reaction, right?